A takes some vectors to 0. Now if it takes a non-zero vector to 0, that means something that's not in here.
Then you can't invert that
Then
vector.
there's no
Right.
inverse. But it is invertible if the only thing that goes to 0, if the whole kernel is just 0. If there's anything more,
Okay.
then it's not invertible.
Okay.
Okay, so that's sort of the background.
It's sort of a grown-up version of the definition of the function.
Yes. These are functions. The kernel is just looking at, it's called the preimage. Everything that gets the preimage of 0.
Okay.
Everything that gets mapped to 0.
Okay.
You've got an image
Okay.
and then you've got its preimage, and this is everything that goes to that one element.
All right, thank you. First time I've really understood that.
Cool. Okay, so similarly, now I'm going to switch my G is going to be O and K, the generalized orthogonal group. This is going to be the group of real numbers. The identity over here is just, I'm going to call it regular 1. It's the regular old number 1. And my phi is the determinant map, which takes the determinant of matrices. All right, so if I look at the kernel of the determinant, that's everything that has determinant 1. It's everything that when I take the determinant map of it, it takes it to 1. So that means that determinant A is 1. So this is the way, this is one way of saying that, so the kernel of so saying that the kernel of the determinant means that the determinant 1. So A is in the kernel of determinant means determinant A equals 1. But that's just the definition. That right here, everything in the kernel is stuff which gets mapped to 1. So you can throw your sticks at people and say, why didn't you just say the determinant is 1? It's the kernel of the determinant map.
But it's more than that.
Okay, so the kernel of the determinant gives us this sub-collection of things over here, which in fact is a subgroup. And it's not relevant, so we don't want to get into the word normal, but it is in fact a normal subgroup. Okay, and this normal subgroup has a special name. It's the special generalized orthogonal group. So kernel determinant, this determinant in particular, is called SONK.
Specialized orthogonal groups.
Yep. And it's really just, it's just O, I'll say guys, okay, just elements and O and K with determinant 1. Okay, that's all we want to see. So I'm halfway through stating the exercise. There are a lot of caveats.
We may have more another week out of this.
But I like this way better than me just trudging forward and having blank stares. I think I look at this often enough that I forget what I didn't used to know.
I have a question. On your matrix, did you mean a negative switch in the second row or no?
No, actually I didn't. And this is, that's a good question because you don't want to be trying that forever. But also, yeah, there's a negative sign here, but this is positive, and this has to do with this, recall that
Sin squared theta, was it cosine squared theta
I think
minus?
it's cosh squared, and yeah, theta minus
Sin squared.
squared theta. That's one.
Or, yeah, that's
Pretty sure that one's the one.
it. Yeah.
If not, it's the other way around, but I'm pretty sure it's cosh squared minus sin squared. So this one has a negative sign, and this is, notice, a squared minus b squared.
Uh-huh.
It's got what you're looking for. Okay, that's what's going on there. And then just like the sines and cosines had a squared plus b squared equals c squared, they had that Pythagorean identity. This has a similar identity but with a negative sign, and that's why we use the hyperbolics. And this is actually a hyperbolic type of geometry. If by hyperbolic geometry you mean you're doing geometry on hyperboloids in 3-space. So I don't know if it's, I don't know the relation to actual hyperbolic geometry. All right. No, I was. Sorry, guys. That actually. This is just. I still need to finish this exercise. Okay, so also show that. So that I don't even know what you're supposed to do over there. It's kind of cluttered now. But really, all you're supposed to do is show this first part.
Show that that is an element of SL1, so you're showing that it meets the requirements of SL11.
That's exactly it. Okay. And here's something really nice, especially if you're a physicist. Also, show that cosh, call it eta 1, sinh eta 1, sinh eta 1, cosh eta 1 times cosh eta 2, sinh 2 sinh eta 2 cosh eta 2. So basically, if I take two products from guys that I know already are in SO11, what I get, well, it's a group, so it better be back in SO11, but what does it look like? And the answer is particularly nice. Okay, it's basically like you're adding
Cosh
angles.
eta 3.
It's cosh eta 1 plus eta 2, sinh eta 1 plus eta 2, sinh eta 1 plus eta 2, cosh eta 1 plus eta 2. So this is actually, I think it's really kind of, every time I see a cosh or a sine, I feel like I'm doing applied math. It's no longer so abstract that I can't touch it. This cosh is, hyperbolic stuff, functions are familiar from calculus. So also show that. And this is, I'll say, challenge, because this is a bit harder. I was able to do it with a little bit of finagling on my own, but this really illustrates something nice. Okay, show that every group element, and it's just O11, can be written in one of the four forms, like this. Well, we know that this is going to be in here. Sinh, if one of these matrices is not symmetric, let me know. They should all be symmetric. Cinches and cinches on this diagonal and coshes on the other diagonal. I might screw that up. Okay, that. I'm just going to do. Theta. This is the same matrix right now. I'm going to throw some negative signs in just a second. Okay. Okay, and then I've got negative signs here, negative signs here, and negative signs here. Okay.